Hello everyone, welcome to this new topic. In this series of videos we are going to go over several different models for regression and prediction problems. This is the first part where we are going to describe the simplest regression model, and then in other videos we are going to see more complex regression models. So what are prediction problems? Every time we must design or train a model to predict a continuous variable, we have a prediction problem, right? So for example, to predict the price of a real estate by using the square meters, the number of bedrooms, the number of bathrooms, the latitude and longitude as inputs, that could be a prediction problem, right? To predict the Bitcoin price given the S&P 500 and Dow Jones indexes together with the current date as inputs, that also could be it is a prediction problem. Or to predict the e-commerce sales by using the online advertisement budget as input, also could be casted as a regression or prediction problem. And something different, right? How to predict how a tumor reacts to a drug using the gene expression information as input. That also could be addressed with a regression model, and it is a prediction problem. So here are some visual examples of what we mean, right? It's basically when we have data, training data, and we want to predict the variable y. Simpler linear regression tries to fit a linear model. Of course, it's extremely simple, we can see here, right? Where with the training points, we learn a model that led us to predict the value of any possible point in the domain. So in one dimension is this, for example, and here we have a two-dimensional plane used as a linear model to predict this variable. Of course, this could be more complex, right? And we can, with the same linear regression approach, but not the simplest case, we can curve the models and have more flexible approximations, right? We're gonna see this later. So, and we can also solve multidimensional regression or prediction problem, right? Where we have a bunch of variables, in this case from 0 to 9 inputs, and the variable y that corresponds to the output we want to predict. So what is the setup of this model? The main assumption is that y, the output variable, can be modeled as a linear combination of the input variables plus an error. So for example, the price could be a linear combination of the input features like rooms and baths plus a random error. We're gonna elaborate on that later. So in math notation, it could be something like this. So the prediction or our estimation of the value of y, it is a function of the input variables plus an error. That is one specific error for this prediction in particular. So in this case, the linear combination has the bias term with the coefficients applied over the different values of x, finally plus the error. And in a more compressed notation, we can use sums, right, to have the same thing. So take a look to these equations and make sure you really understand them very well. At the beginning might look like complex, but it's the same thing, just in more general perspective. So in the same way, we can use matrix representation for the regression setup. The y that corresponds to the output column in our data could be represented as a column vector the X matrix contains all the input variables as rows in a matrix. This column of ones is just the term that allows us to multiply X with W such that the bias term beta 0 is going to be free. It's not going to be multiplying any of the X's. And finally, the model, right? The W we are trying to find also could be represented as a column vector. So how we find the model? In the regression setup, in the simplest case, what we want to minimize is the difference between the real values of the output and the predictions. So in this case, for example, the real values are the training cases that come in our database, in our training set. And then we have the estimations, right? The y hats. And we want to compute basically that difference, and we want to minimize that. So recall that each of these y hats are linear combinations of the inputs. In this case, we're using 9 just in this example in particular, right? But this could be extended to any dimensionality. Okay, so this, recall that could be represented as matrices, right? Where that square difference can be represented as a multiplication between this y minus the linear combination of the x's transposed times the same thing, right? And recall that this is the error. So we are assuming that it's going to be an error or a difference between our prediction and the real value in the training set, of course, because we are using a much simpler model. So we call this the RSS, or residual sum of squares, right? And this is what we want to minimize. So in order to minimize the RSS, we need to get the derivatives with respect to W, which is the thing we want to find, right? And then we need to equalize it to 0. So the derivative is basically that. You can check by yourself. It's just basic algebra to find the derivative of this RSS. The minus 2 comes from the square, and the minus from this term, right? And if we set that to 0, then we can easily find W as this product. Summary so far. So we have one thing first, is like we have training data. It means like the input variables in the matrix X and the output variable Y. Then with X and Y, we can estimate W with the equation we saw previously. So then with W, we already can make predictions for new data. So for example, if we get new input variables with an unknown output Y new, we basically just need to multiply the input variables by W, and then we're going to get the output predictions. Some things we must consider. Besides this assumption that in linear regression, the output variable is a linear combination of the input variables, we have some others. For example, the error or of each prediction and observation point is independent across all the other points. So for example, here, if we have this model that was trained or found by using the orange training points, then we get all those errors, right? Those errors are all independent among them. It means that if error 3 has a specific value, or we found a specific value for that, that will not affect at all the value of the error 4. Also, we are in simple linear regression, we assume that the errors have a distribution, a normal distribution with mean 0 and variance sigma square. So this means that for every prediction, for example, if we want to predict the value of xi, then the prediction is going to be a normally distributed value centered in the xi times w with a variance equal to sigma square, as we can see in the figure. So now this is going to be exactly the same for all the points we want to predict. All our predictions are going to be independent normal distributions with the same variance but with different mean. Besides that, simple linear regression assumes that the matrix product x transpose times x has inverse. Why? Because of this equation, right? The equation to find w is assuming that this product has inverse. What it means, in other words, it means that all the columns in x must be linearly independent, because if there is any redundant column, in other words, like a redundant variable in our input variables, that product is not going to have inverse, and then we're going to end up with infinite solutions instead of one solution.